So in this video we'll solve the sums of class 12 physics chapter 10 magnetic fields due to electric current. Let's look at the first sum. A piece of straight wire has mass 20 grams and length 1 meter. It is to be levitated using a current of 1 ampere flowing through it and a perpendicular magnetic field B in a horizontal direction. What must be the magnetic field B? So solution, we have a straight wire of length 1 meter and of mass 20 grams. So the weight of the wire will be mg in the downward direction, and it is to be levitated when it is placed in a magnetic field B and when current of 1 ampere is passing through it. So to levitate this wire, the magnetic force should be in the opposite direction to the weight mg. So we can say that the magnetic force is given by BIL sine theta. Now they have clearly mentioned here that the magnetic field is perpendicular to the current. So if the current is in this direction, magnetic field is perpendicular to this. So theta is 90 degree and sine 90 is 1. So we can say that the magnetic force is BIL. Now this force will be in equal and opposite direction to the weight of the wire, that is mg. So we can say that this force Fm is equal to mg, which implies mg will be equal to BIL. From this equation we can say that magnetic field B can be written as mg upon IL. So mass is given to us as 20 grams. That means 20 into 10 raised to minus 3 kg into acceleration due to gravity, that is 9.8 meter per second square, divided by current, which is 1 ampere, into length of the wire, that is 1 meter. Now solving this, we get magnetic field to be 0.196 Tesla. I hope you understood this sum. Let's look at the second sum. Calculate the value of magnetic field at a distance of 2 cm from a very long straight wire carrying a current of 5 ampere. So we have a long straight wire in which current I is flowing of 5 ampere, and due to this current a magnetic field is generated, which is given by B, and we need to calculate the magnetic field at a distance of 2 centimeter away from the wire. So let's take this distance as 2 centimeter. So we know the formula for a magnetic field at a distance r when current I flows through it is given by B equal to mu naught I upon 2 pi r. So here r is 2 centimeter, that is 2 into 10 raised to minus 2 meters, and I is given to us as 5 ampere. So putting all this value, and we know mu naught is 4 pi into 10 raised to minus 7 Weber per ampere meter. So the magnetic field will be 4 pi into 10 raised to minus 7 into current is 5 ampere divided by 2 pi into the distance is 2 into 10 raised to minus 2 meter. So solving this, we get magnetic field to be 5 into 10 raised to minus 5 Tesla. Let's look at the next sum. An electron is moving with a speed of 3 into 10 raised to minus 7 meter per second in a magnetic field of 6 into 10 raised to minus 4 Tesla, perpendicular to its path. What will be the radius of the path? And what will be the frequency and the energy, that is the kinetic energy, in kilo electron volt? Given to us is the mass of electron, charge of electron, and value of 1 electron volt in joules. So solution, the velocity of the electron is given to us as 3 into 10 raised to minus 7 meter per second, and the magnetic field B is given to us as 6 into 10 raised to minus 4 Tesla. And we need to calculate first of all the radius, then frequency, and the kinetic energy in kilo electron volt. So let's calculate this. Using the cyclotron formula, we have mv equal to qbr, that is, when a charge is placed in a magnetic field, it traces a circular path of radius r. From this we can say that r will be, that is the radius of the circular path will be mv upon qb. Putting all the values, we have mass of electron to be 9 into 10 raised to minus 31 kg into velocity of electron, that is 3 into 10 raised to minus 7 meter per second, and charge of electron is 1.6 into 10 raised to minus 19 into the magnetic field in which the electron is placed, that is 6 into 10 raised to minus 4 Tesla. Now solving this by using log, we get the radius to be 0.2812 meters. Next thing they have asked us is the frequency. So we know frequency can be given by F equal to QB upon 2 pi m. So again putting all this value, 1.6 into 10 raised to minus 19 into 6 into 10 raised to minus 4 divided by 2 into 3.142 into mass, that is 9 into 10 raised to minus 31, and solving this using log, we get frequency to be 16.97 into 10 raised to 6 hertz, which can be written as 16.97 megahertz. Lastly, what we need to find out is the kinetic energy in kilo electron volts. So we know the formula for kinetic energy is half mv square. So putting all this value, that is half into 9 into 10 raised to minus 31 into v square, that is 3 into 10 raised to minus 7. So 3 into 10 raised to minus 7 square, and solving this we get kinetic energy to be 40.5 into 10 raised to minus 17 joules. But we need this kinetic energy in kilo electron volt. So we know that 1 electron volt is 1.6 into 10 raised to minus 19 joules. To convert this value in electron volt, we need to divide this kinetic energy with 1.6 into 10 raised to minus 19. So kinetic energy will be 40.5 into 10 raised to minus 17 divided by 1.6 into 10 raised to minus 19 electron volt, and solving this we get 2.531 into 10 raised to 3 electron volt, so which can be written as the kinetic energy to be 2.531 kilo electron volt. I hope you understood this sum. Let's look at the next sum. An alpha particle, that is the nucleus of helium atom with charge plus 2, is accelerated and moves in a vacuum tube with kinetic energy 10 mega electron volts. It passes through a uniform magnetic field of 1.88 Tesla and traces a circular path of radius 24.6 centimeter. And we need to obtain the mass of the alpha particle. So solution. So first of all, we have been given the kinetic energy, which is 10 mega electron volt. So let's convert this into joules. That will be 10 into 10 raised to 6 into 1.6 into 10 raised to minus 19 joules. And solving this we get 1.6 into 10 raised to minus 12 joules. Now the magnetic field B is given to us as 1.88 Tesla. Also the radius of the circular path is 24.6 centimeter, which can be written as 24.6 into 10 raised to minus 2 meters. And since this is an alpha particle with charge plus 2, the charge will be 2e, that is 2 into 1.6 into 10 raised to minus 19, which can be written as 3.2 into 10 raised to minus 19 coulomb. Now again from the cyclotron formula, mv equal to qbr, we have velocity to be v equal to qbr upon m. Now putting this value in the kinetic energy equation, that is kinetic energy equal to half mv square, putting the value of velocity here, we get q square b square r square upon 2m. From this we can say that the mass m will be q square b square r square divided by twice the kinetic energy. Now let's put all this value, that is q square, that will be 3.2 into 10 raised to minus 19 square into 1.88 square into radius is 24.6 into 10 raised to minus 2. So 24.6 into 10 raised to minus 2 square divided by twice the kinetic energy, that is 1.6 into 10 raised to minus 12. And solving this we get mass to be 6.844 into 10 raised to minus 27 kg. So I hope you are also getting the same answer by calculation. Let's look at the next sum. Two wires shown in this figure are connected in a series circuit, and the same amount of current of 10 ampere passes through both the wires but in opposite direction. Separation between the two wires is 8 millimeters. That is, between this AB point and the wire 2 we have a separation distance of 8 millimeter. The length AB, that is the S, is given to us as 22 centimeters. Obtain the direction and magnitude of the magnetic field due to the current in wire 2 on the section AB of wire 1. Also obtain the magnitude and direction of the force on wire 1. So solution. So first of all, let's calculate the magnetic field due to the current that is passing in wire 2 on the wire 1. That is, if current I is going in this direction, so magnetic field will be in clockwise direction according to right hand rule, that is inside the plane negative z direction. So let's calculate the magnitude of this magnetic field. So we know magnetic field B is given to us as mu naught I, that is the current in wire 2, divided by 2 pi d, that is the distance between the two wire, which is 8 millimeter. So d is 8 mm, which can be written as 8 into 10 raised to minus 3 meters, and current I is given to us as 10 amperes. So let's put all this value and calculate first of all the magnetic field. So mu naught is given as 4 pi into 10 raised to minus 7 into current is 10 ampere divided by 2 pi into d is 8 into 10 raised to minus 3. So 2 pi 4 pi gets cancelled, and this becomes 2 into 4, and 4 divided by 10, that is 2.5. So this will come out to be 2.5 into 10 raised to minus 4 Tesla. So this is the magnetic field due to current in wire 2 that must be experienced by the wire 1 in negative z direction. Now secondly, they have asked us to find the magnitude and direction of the force on wire 1. Now we all know that for parallel current the force is attractive, and for anti-parallel current the force is repulsive. So here in wire 1 current I is going in upward direction, and in wire 2 the current I is going in downward direction. So the currents are anti-parallel, so the force between them will be also repulsive. Now let's calculate the magnitude of that force. So F is given to us as mu naught I1 I2 into L, that is the length of the wire. So for us the length will be 22 centimeter, because we need to calculate only for this part A and B, divided by 2 pi d. So let's put all this value. We get 4 pi into 10 raised to minus 7 into I1 and I2 both are 10 amperes, so 100 into L, the distance is 22 centimeter. So 22 into 10 raised to minus 2 divided by 2 pi into 8 into 10 raised to minus 3. So cancelling this and this also gets cancelled. We'll have 44 divided by 8, which will give us the repulsive force to be 5.5 into 10 raised to minus 4 Newton, and this force is repulsive since the currents are anti-parallel. I hope you understood this sum. Let's look at the next sum. A very long straight wire carries a current of 5.2 ampere. What is the magnitude of the magnetic field at a distance 3.1 centimeter from the wire? So there is a wire which carries a current which is 5.2 ampere, which generates a magnetic field B in anti-clockwise direction suppose, and we need to calculate the magnitude of the magnetic field at a distance r, which is 3.1 centimeter from the wire. So we know B is given to us as B equal to mu naught I upon 2 pi r. So 4 pi into 10 raised to minus 7 into current is 5.2 ampere divided by 2 pi into r is 3.1 centimeter, that is 3.1 into 10 raised to minus 2 meters. So solving this we get B to be 3.35 into 10 raised to minus 5 Tesla. I hope you understood this sum. Let's check out the next sum. Current of equal magnitude flows through two long parallel wires having separation of 1.35 centimeter. If the force per unit length on each of the wire is 4.76 into 10 raised to minus 2 Newton, what must be the current I? So there are two long wires in which current I flows of equal magnitude and the same direction. They are separated by a distance of 1.35 centimeter, and the force per unit length, that is F upon L, is given to us as 4.76 into 10 raised to minus 2 Newton. We need to calculate the value of I. Now we know that for two parallel current carrying wire, the force is given to us as F equal to mu naught I1 I2 into L divided by 2 pi d. So F upon L, that is force per unit length, will be mu naught, and since both the currents are same, so I can say write this as I square divided by 2 pi d. And now we need to calculate I. So taking I square one side and all these value on the other side, we get I square to be F upon L into 2 pi d upon mu naught. So we have the value of force per unit length, we know the distance between the two wires, and we know the value of mu naught. So I square will be 4.76 into 10 raised to minus 2 into 2 pi into distance is 1.35 into 10 raised to minus 2 divided by mu naught, that is 4 pi into 10 raised to minus 7. Solving this, we get I to be 56.7 ampere. I hope you understood this sum. Let's check out the next sum. Magnetic field at a distance of 2.4 centimeter from a long straight wire is 16 microtesla. What must be the current through the wire? So solution, magnetic field is given to us as 16 microtesla, which is 16 into 10 raised to minus 6 Tesla at a distance d 2.4 centimeter, which can be written as 2.4 into 10 raised to minus 2 meters. We need to calculate what must be the current that has generated this magnetic field. So we know the magnetic field is given to us as mu naught I upon 2 pi d, which implies I can be written as b into 2 pi d divided by mu naught. So putting all this value, 16 into 10 raised to minus 6 into 2 pi into the distance is 2.4 into 10 raised to minus 2 divided by mu naught, that is 4 pi into 10 raised to minus 7. Solving this, we get the current to be 1.92 ampere. Let's check out the next one. The magnetic field at the center of a circular current carrying loop of radius 12.3 centimeter is 6.4 into 10 raised to minus 6 Tesla. What will be the magnetic moment of the loop? So solution. So we have a current carrying loop. This is the axis. This is the center, and radius is given to us as 12.3 centimeter. This has a magnetic field B equal to 6.4 into 10 raised to minus 6 Tesla, and we need to calculate the magnetic moment M. So since they have asked us at the center of the circular loop, so the distance on the axis Z will be equal to 0 for it to be at the center. Also the radius R is given to us as 12.3 centimeter, which can be written as 12.3 into 10 raised to minus 2 meters. Now we know that the magnetic field at an axis for a current carrying loop is given to us as B equal to mu naught I R square divided by 2 into Z square plus R square 3 by 2. Since Z is 0, this will be mu naught I R square divided by 2 R. Now since Z is 0, so R square and 3 by 2, it will be R cube. Now keeping it as it is, we know that magnetic moment M is given to us as NIA. N is the number of turns. So since it has only one turn, N will be 1. So M will be IA. Now A is the area of the circular loop, that is pi r square. So I into pi r square. So M is I into pi r square. Now if we multiply this equation with pi up and down, we'll get mu naught I pi r square divided by 2 pi r cube. Now we know that I pi r square is magnetic moment m. So this formula can be written as mu naught m upon 2 pi r cube. Now from this we have B equal to mu naught m 2 pi r cube, which implies the magnetic moment that we need to find out m can be written as B into 2 pi r cube divided by mu naught. Now let's put all these value. 6.4 into 10 raised to minus 6 into 2 pi into r cube, that is 12.3 into 10 raised to minus 2 the whole cube divided by mu naught, that is 4 pi into 10 raised to minus 7. And solving this we get magnetic moment m to be 5.954 into 10 raised to minus 2 ampere meter square. I hope you got this sum. Let's check out the last sum of this video. A circular loop of radius 9.7 cm carries a current 2.3 ampere. Obtain the magnitude of magnetic field, first at the center of the loop and second at a distance of 9.7 cm from the center of the loop but on the axis. So solution. So for the first part we have been given a circular loop of radius 9.7 centimeter which carries a current of 2.3 ampere, and we need to find the magnitude of magnetic field at the center of the loop. Now since this loop has only one turn, so n will be 1. Now the magnetic field for a current carrying loop is given to us as mu naught n I upon 2r. Since n is 1 and putting all the other values, we get 4 pi into 10 raised to minus 7 into 1 into current is 2.3 ampere divided by 2 into radius, that is 9.7 centimeters. So 9.7 into 10 raised to minus 2 meters. And solving this we get magnetic field at the center of the loop to be 1.49 into 10 raised to minus 5. Now in the next case they have asked us to find the magnetic field at a distance of 9.7 centimeter from the center of the loop but on the axis. So if this is a circular loop and this is the axis of radius r 9.7 centimeter, we need to find the magnetic field on the axis of distance from the center to be 9.7 centimeter. So let's take this value as z, this value is r. So the formula for magnetic field on the axis is given to us as B equal to mu naught I r square divided by 2 into z square plus r square the whole 3 by 2. Here value of z and r is equal, that is 9.7 centimeter, which can be written as 9.7 into 10 raised to minus 2 meters. So since this is same, we can write this as mu naught I r square. I can write z square as r square, so this will be 2r square. So 2 into 2 3 by 2 into 2r square, that will be r cube. So r square and r cube gets cancelled. We have mu naught I divided by 2 raised to 3 by 2 can be written as 2 into 2 root 2 into r. Now let's put all the value, that is 4 pi into 10 raised to minus 7 into current I, that is 2.3 ampere divided by 4 into root 2, that is 1.414 into radius, which is 9.7 into 10 raised to minus 2. So solving this we get the magnetic field on the axis at a distance 9.7 centimeter from the center to be 5.267 into 10 raised to minus 6 Tesla, which can be written as B equal to 5.267 micro Tesla. So thank you for watching this video, and we'll solve the remaining sums in the next part of this video.